In 2009, Stephen Hawking organized a party at his office in Cambridge, complete with champagne, decorations and handwritten invitations. But the invitations were not sent out beforehand. Instead, Hawking waited until the party was over before publicly announcing the date, time and location of his event. His idea was that if time travel to the past were possible and if future humans had mastered it, then time travelers could, at least in principle, attend the party. No one came, no visitors from the future. Hawking later revealed the experiment on television, presenting it with his characteristic dry humor. Although not a rigorous scientific test, the experiment made a serious point. There is no empirical evidence that backward time travel is possible, at least not in a way that allows macroscopic objects or people to return to the past. But if we assume that time travel is possible both ways, forward and backward, how would it work? What would time travel laws look like? With our current understanding, can we work out all the mechanics of time travel? Time travel is the idea that movement through time, past or future, might be possible, just as movement through space is. In everyday life, we experience time only flowing forward. We grow older, memories accumulate, and causes always seem to precede effects. But imagination refuses to obey this rule. Long before science took it seriously, storytellers dared to ask, what if time could bend? One of the earliest and most influential visions came from H.G. Wells, who, in The Time Machine, imagined a device that could slide freely along the timeline. Wells did not explain how such a machine worked, as his story was less about mechanics and more about consequences. If one could visit the future, what would humanity look like? If one could return to the past, could history be changed? Decades later, science began to take the idea seriously. In 1905, Albert Einstein published his theory of special relativity, quietly transforming our understanding of time. According to Einstein, time is not absolute. It stretches and slows depending on how fast you move. A clock on a fast-moving spacecraft ticks more slowly than one on Earth. This phenomenon, called time dilation, has been experimentally verified using atomic clocks on aeroplanes and satellites. In a limited but real sense, we are already time travelers, moving into the future at slightly different rates. General relativity deepened the mystery. It showed that massive objects bend spacetime itself, raising theoretical possibilities such as wormholes, shortcuts through spacetime that might connect different times as well as places. Physicists like Kip Thorne have explored whether such structures could allow backward time travel without violating any laws of physics. The answer remains uncertain and controversial. Time travel disturbs the fundamental understanding of our universe. It messes with causality. Causality is the rule that stitches reality together. Causes come before effects. A stone breaks a window. The window does not break itself in anticipation. In physics, causality is a real structural constraint. Without it, prediction collapses, logic dissolves, and science becomes impossible. Time travel threatens this structure not by bending it but by looping it back into itself. Before the 20th century, causality felt secure because time itself felt absolute. Events marched forward in a single file, the same for everyone. Then again, Einstein replaced this comforting picture with space-time, where time could stretch, slow, and differ between observers. Yet even here, causality survived. Space-time was divided by light cones. Only events inside your past light cone could affect you. Only events inside your future light cone could be affected by you. Faster than light signals and effects without causes were forbidden. Time travel enters the story when spacetime itself allows shortcuts. In certain solutions of Einstein's equations, paths called closed time-like curves appear, world lines that bend so severely that they return to their own past. One of the first to take this idea seriously was Kurt Gödel, who found a mathematically valid universe in which time loops naturally existed. Nothing exotic was required, no broken equations, just an unsettling conclusion. Physics did not automatically forbid traveling into yesterday. But going back to the past has its problems. It is not easy as going back to a place you have just visited, but rather going back in time in many ways fractures the solid reality we live in. The most famous fracture is the grandfather paradox. Suppose a traveler goes back in time and kills their grandfather before their parent is born. If the grandfather dies, the traveler is never born. But if the traveler is never born, they cannot travel back in time to commit the act. Logical contradictions do not only arise when we travel in time. The transportation of anything can lead to a paradox. Imagine discovering a set of equations that allow you to build a time machine. Years later, after the machine works, you travel back in time and hand those same equations to your younger self. The loop closes, but a disturbing question remains: who originally created the equations? This is the bootstrap paradox, also called the ontological paradox. It arises in discussion of backward time travel when an object, piece of information, or event exists in a closed causal loop. The effect becomes its own cause. Unlike the grandfather paradox, the bootstrap paradox contains no logical contradictions. The timeline is perfectly consistent, yet something essential is missing: an origin. A particularly clear illustration of how paradoxes can arise even when only information and not physical object is sent backward in time comes from the hypothetical existence of tachyons, particles that move faster than light. Relativity leaves no ambiguity in this point. Anything traveling faster than light would, in some reference frame, move backward in time. If tachyons were real, they could not be used for communication without creating contradiction. Physicists G. A. Benford, D. L. Book, and W. A. Newcomb have pointed out that this consequence is often overlooked by researchers searching for such a particle. In their discussion of the tachyon antitelephone, they show that certain experimental interactions proposed to detect tachyons would in principle allow messages to be sent into the past. To illustrate this, imagine a physicist on Earth communicating via tachyonic antitelephones with another physicist in a distant galaxy. They agree on the following rule: the distant physicist will immediately reply to any message received. The physicist on Earth promises to send a message at 3 o'clock Earth time if and only if no reply has been received by 1 o'clock. Here is the problem. Both the original message and the reply can travel backward in time. If the Earth physicist sends the message at 3, the reply could arrive before 1. This could mean that the message is sent if and only if it is not sent, a direct and unavoidable violation of causality. As the authors conclude, this setup produces a genuine causal contradiction. As we think more about time travel, another kind of logical contradiction arises. Suppose a time traveler goes back in time to stop a disaster, only to discover that their own actions are exactly what caused it. This unsettling loop is known as the predestination paradox. Unlike the grandfather paradox, which creates a contradiction, the predestination paradox is perfectly consistent. The timeline never changes, it completes itself. At the core of the paradox is a closed causal loop. An event in the future causes an action in the past, which in turn causes the same future event. There is no point at which the chain can be altered, because all attempts to interfere becomes part of history rather than a deviation from it. The traveler does not rewrite the past, they fulfill it. In physics, this idea aligns with the Novikov self-consistency principle, that if time travel to the past is possible, only those events that are globally consistent can occur. A time traveler may act freely, but the outcome of those actions are constrained so that no contradiction arises. The universe behaves like a completed story. You can read it in any order, but the ending does not change. The predestination paradox challenges our intuition about free will. If the past already includes the traveler's actions, then choices may seem real but powerless. Yet, causality remains intact. Nothing contradicts itself. Ultimately, the predestination paradox suggests that the deepest danger of time travel is not chaos, but inevitability. All time travel paradoxes, or at least the majority of it, whether it is the grandfather paradox, bootstrap paradox, or the predestination paradox, arises from the same source, a breakdown of causality. In one case, an effect destroys its own cause. In another, an effect exists without any cause at all. In the third, cause and effect lock into an inescapable loop. To physics, these are not only strange stories, they are signs that a theory has lost predictive power. Modern physics, from Albert Einstein's light cone structure to quantum probability, is built on the assumption that causes reliably happen before effects. When time travel allows information or events to move backward, the structure collapses. Equations stop giving unique answers, conservation laws become ambiguous, and probabilities no longer make sense. This is why physics either restricts time travel through self-consistency rules or forbids it entirely, as suggested by Stephen Hawking's chronology protection conjecture. The universe, it seems, tolerates strange phenomena, but not logical contradiction. Paradoxes are not mystery to be embraced, they are warning signs that reality refuses to allow its own history to be rewritten. Time travel endures in science fiction precisely because it sits at the fault line between what physics allows and what human imagination refuses to abandon. Where real science treats time travel paradoxes as a sign of theoretical breakdown, fiction treats them as opportunities for meaning. The same paradoxes that physics tries to eliminate, the grandfather paradox, the bootstrap paradox, and the predestination paradox, become narrative engines rather than logical failures. Modern physics is built on causal order, but the paradoxes signal that predictions, conservation, and probability have stopped making sense. Science must close these loopholes, because a universe that allows contradictions cannot be mathematically described or experimentally tested. instead. Science fiction, however, is not bound by the need for predictive consistency. Its goal is not to preserve causality, but to interrogate it. Time travel allows writers to externalize inner human conflicts. Regret becomes a destination, guilt becomes a journey, and fate becomes a character. A grandfather paradox is not just a logical puzzle, it is a story about responsibility. A bootstrap paradox is not about missing origins, it's about meaning without authorship. A predestination paradox is not about inevitability alone, but whether choice still matters when outcomes are fixed. Crucially, time travel also dramatizes the tension between scientific knowledge and human desire. Even if physics suggests that past cannot be changed, fiction asks what it would feel like to try. Even if paradoxes imply impossibility, stories use them to test moral boundaries rather than physical ones. In doing so, science fiction keeps the conversation alive between what the universe permits and what humanity longs for. Time travel remains popular not because it is plausible, but because it is powerful. It turns limits of physics into questions about identity, agency, and consequences. Where science draws boundaries, fiction explores what those boundaries mean and why we keep pressing against them. Perhaps time travel paradoxes exist not because time itself is flawed, but because our assumptions about it are. We instinctively imagine time as a road, something that can be traveled forward or backward like space. Yet, the universe may not permit such freedom. Time may be a structural feature of reality, not a dimension we can navigate at will, but a constraint that defines how events are allowed to unfold. Or the problem may lie not with time, but with us. Human logic evolved to survive a narrow slice of reality, where causes reliably precede effects and contradictions never occur. When we apply the same intuition to the cosmos, it begins to fail. At extreme scales, near light speed, black holes, or hypothetical time loops, our everyday notion of cause, choice, and sequence may no longer apply. In this view, time travel paradoxes are not puzzles demanding solutions, but signals making a boundary of understanding. They remind us that the universe is under no obligation to fit comfortably within human reasoning. What we call paradox may simply be the shadow cast when limited logic encounters a deeper, unfamiliar order of reality.